So, we have on the Google site a section about aqueous equilibria. You can go there for lesson resources. So if we open up lesson 1, I've recommended the following work to be done for homework. So there's the recommended 2 pages out of this iPad, which we'll spend some time doing in class after we go over this portion right now. And also 2 recommended activities from Education Perfect. So the links take you right to those activities. You might have got an email from me, a scary email just 5 minutes ago that says Education Perfect has assigned like 5 hours worth of aqueous equilibria to do. That's the bulk. That's the bulk work I want us to accomplish over the next few weeks, okay? And so the recommended tasks are what I recommend you to do during the lesson of the day, but you could work ahead if you wanted to and work on that bulk tasks I've assigned if you want to at your own pace. Cool? And the slides for today are up here for those who'd like to follow along. Solomon, are you able to view them, or have I locked them?
No, you can view them.
Sweet. Thanks, Archie. Okay, so let's get started with today's lesson. Now, equilibria was a topic we spent a few weeks on last year, but we're looking at specific types of equilibria this year. So, sure, chemical reactions happen in equilibrium sometimes, but there's specific types of them. Similar to how there's specific types of enthalpy changes. Remember back then we looked at enthalpies of formation and combustion and all that stuff. This is kind of analogous. This is specific types of equilibria, just like how there's specific types of enthalpy changes. So today we're looking at one topic about sparingly soluble solids. So solids that kind of don't really dissolve well. We say, you could call them precipitates, right? That word will come up a lot. They're precipitates. They're solids that don't really dissolve, but a little bit of them does. And there's an equilibrium between the amount that does dissolve and the bulk solid in a solution that actually doesn't. So we're looking at often transition metals forming precipitates. You could look at silver precipitates, anything like that. And we're looking at how much actually dissolves. This is useful because if we're looking at water quality, and we know that there are some heavy metals that we want to monitor the concentrations of in our water, one way of removing some dangerous metals from our water is to precipitate them out. If we add hydroxides or anything else that would precipitate those metals out, and then we could calculate actually, even though it's precipitated out, we know some amount of that dangerous metal might actually dissolve into the solution, and we need to be able to calculate how much of that is actually left in that equilibrium between the precipitate and the amount that's actually still dissolved. Before we get into that, I want to show you something funny I saw on the chemistry memes Reddit the other day. This is a water bottle that claims by fusing 2 O2 molecules together, they've created the molecule O4. And it ensures there's 100 times more oxygen in this regular water, guys. O4 is not a thing. I have no idea where the claim that there's 100 times more oxygen in there. Yeah.
I want to know where the asterisk goes then.
So are they claiming it's H2O4?
No, they're
No, just O4.
Because the idea is they're marketing as if you drink this, you're supplying your body with lots of oxygen. The oxygen in the water will be taken up by your body. So if you're recovering from exercise, your body's got a lot of O2 in it now, right? Or I guess O4. That's not a thing.
Oh, natural water.
Maybe.
So let's get into actual chemical equilibria. We know this deals with a topic called reversible reactions. So we know reversible reactions will eventually reach a point where both the forward rate of that reaction and the reverse rate of that reaction happen at the same rate. This is called equilibrium, when the forward and reverse rate are equal. It's often called dynamic equilibrium because it looks like nothing's happening in the solution. But remember, there's constantly products turning into reactants and vice versa. It's still ongoing. So even though it looks static, we use the word dynamic because chemical reactions are still happening both ways. Make sense? Thumbs up. Cool. So with reversible reactions, we know that there's no observable change in the mixture when equilibrium's been achieved. It's the rate that's equal. And the reactants and products don't necessarily have the same concentrations at equilibrium. That's important, right? So the rates are equal, but you still at equilibrium might have a heap more product than reactant. or vice versa. And that's what the graph's showing here. With concentration on the y-axis, we see that initially, of course, 100% of what we've got must be reactants. And then over time, we form lots of products. And maybe at equilibrium, when the rates are constant, we have more product than reactants. But the other could be true as well. We start with lots of lots of reactant, but over time, at equilibrium, maybe we still have more reactant than product. That's okay, that's another scenario. But they're not necessarily going to be equal. We did that water demo last year, right? Anyone remember? Yeah, sweet. Mm-hmm. Where I got some volunteers up and using different sized beakers to transfer water from one container to another. And eventually, one person is transferring a lot more water than the other because one has a larger beaker, the other one has a smaller one. But eventually, the person with that large beakers transferred over most of their water, and they can only scoop up a little amount. And we compared the amounts that they're transferring, and after a time, they compared the volume of water in their beakers, and they said, even though you got different size beakers, the amount you're transferring is the same. So that means the rate you're transferring is the same. You're at equilibrium. The water levels stay the same. So we don't need to redo that demo, but the video's there. It's a good analogy. So let's actually get into the chemistry of it. We're able to write equilibrium constant expressions. So it's a ratio of products to reactants at equilibrium. We called the expression constant Kc last year. And the value gives an indication of the amounts of products to reactants because it is a ratio of products to reactants. So if that Kc value is a large number versus a small number, that tells us something about the reaction and the relative quantities of products to reactants.
Is this the thing where if Kc is equal to 1 or over 1, greater than?
Yeah.
If it's at 1, that means they're both equal. If it's greater than, more product?
Yeah, you got it. That's exactly right. Because if it's greater than 1 and the ratio is products divided by reactants, if it's a number greater than 1, that numerator, where the products are, must be more abundant. Just writing on the board here, products over reactants for our Kc expression. So once again, that's our ratio, right? And more specifically, in the general sense, we see it's a ratio of our products C and D in this example over our reactant concentrations A and B. And remember, if there are any stoichiometric coefficients, we make sure we put the concentrations of our products and reactants to the power of that coefficient. So in the case of this Haber process forming ammonia, we make sure we square the concentration of ammonia here in the numerator. And we've also raised the power of hydrogen to the power of 3 in the expression here. And yeah, what you're saying, Annabelle, is that because it's a ratio of products to reactants, if it's equal to 1, if the Kc is equal to 1, that means they're equal in terms of their concentrations. Cool.
Which way around does it go if it's greater than 1 and less than 1?
So if Kc is greater than 1,
there are more.
It was what you said earlier, products
Okay.
is more abundant. Yeah. Products greater than reactants.
Yeah.
And vice versa. And this was a little picky thing I mentioned last year, but it's really important today. Only reactants that are gases or aqueous are included in these expressions. We don't include solids or liquids because their concentrations don't change. You might think that doesn't make sense, but if you have...
Change in temperature or something, wasn't it?
Pardon?
I'm trying to remember what it was. It was something like when you change the temperature of a solid, it doesn't change the state of it or something like that.
It has to do with the fact that the concentration stays the same.
Yeah, there we go.
The concentration stays the same because if you imagine like pool balls or something like that, you've got like a pyramid of spheres here, okay? So you've got a certain amount of mass in a certain volume, right? The shape of the stacked tower here. If you take one away, sure, you have less mass, but you also have less volume. So the ratio is still the same. With a solid, as it gets consumed in a reaction, the concentration stays the same because even though you take some mass away because it's been consumed, the total volume it occupies has decreased as well proportionally. So we say the liquid and solid concentrations are typically the same. Often there's a huge excess of it too. Yeah.
Is there a symbol for equilibrium? So you have to just keep writing equilibrium over
It's the arrow.
He's just talking about a shorthand for writing the word. I just write equilibrium sometimes, if you want to. Okay, so we're looking at solubility equilibrium today, right? The idea that some solids are sparingly soluble. Not all ionic compounds actually dissolve. Some don't at all, really. So we know the term solute and solvent, right? So solvent is the liquid that we're putting a solute into, something that we want to hopefully dissolve. It's often a compound we're putting into water, right? But the solvent doesn't necessarily need to be water. A lot of organic chemistry, we're looking at other non-polar and polar solvents, like acetone, that sort of thing. So we know what solutes are. They go into the solvent. Now, for a solute to actually dissolve, this is important when we're looking at things that don't dissolve really well. You might be asking, why don't they dissolve really well? This is good scholarship thinking too. For a solute to actually be able to dissolve, it needs to ensure that the attraction between the solute particles and the solvent molecules, that attraction needs to be stronger than the bonds holding the solute together, right? So if you want something to dissolve in water, the water must have a strong attraction to that ionic compound you want to dissolve in it. It must be stronger than the ionic attraction between the cations and anions in that ionic compound. Right? We want to break that electrostatic attraction holding those ionic particles together if we want it to dissolve in water.
So the attraction between the solute and the solvent has to be greater than the part.
The attraction between the solute particles. We want that attraction to be greater than the ionic bonding strength between those ionic particles. And water does a good job as a polar solvent. It's got that electronegative oxygen which can rip out the cations. And it's got those electropositive or really strong partial positive charges on the hydrogens to rip out the negative ions. So the dipoles on the water molecule are really beneficial for that. This is just a short graphic. This isn't too important. This is pretty intuitive. That when we're looking at the equilibrium that's established between these solids that partially dissolve, equilibrium is reached when the rate at which the ions turn back into a precipitate matches the rate at which that precipitate dissolves and forms some ions, right? So this shows initially we drop a solid into a beaker of water. It starts to release some particles into the water as some of it dissolves. And then over time, we reach a rate where the rate that the particles rejoin the solid and precipitate out matches the rate at which they dissolve. And that is the equilibrium we're talking about today. The equilibrium when that rate of dissolving matches the rate of precipitation. And we say that this is a physical change. This isn't a chemical reaction happening. It's not reacting with water molecules. It's simply dissolving. And dissolving is a physical change. Cool. So, we know that a small portion of these solids will actually dissolve. We say sparingly soluble, sparingly meaning just a little bit. So that's what we're going to look at today. And you see our first sparingly soluble chemical equilibrium equation here, where we are producing silver ions from our solid. It's balanced, so it's a stoichiometric ratio of 2 to 1 here between our precipitate and our silver ions formed. And we also form anions when it dissolves. We're using the equilibrium arrow because it goes both ways. We've got to always use those arrows for this unit. Cool. And as it says there, it just says what I've just said, that it's a physical change, right? So we're writing these chemical equations, but it's considered a physical change, not a chemical reaction. We're going to do some basic maths right now. Read that top sentence there. At room temperature, the solubility of this silver chromate compound is 6.5 times 10 to the negative 5 moles per liter. Is that a big or small number? Yeah, 10 to the negative 5, very small number. So that tells us it is a sparingly soluble solid. Now the question in bold is, what is the concentration of those silver ions and the chromate ions in 500 mils of a solution? Okay. Well, I know the solubility. The solubility is a fancy way of saying this is how much dissolves. That's how much of it dissolves. Not a lot, right? That's a very small number, so not a lot. Now with that balanced equation, we can help determine the concentrations of the ions formed. So the equation shows that for every 1 mole of solid that is able to dissolve, it produces 2 equivalents of silver and 1 equivalent of the chromate ion. Cool? So if 2 moles of silver are formed, then the concentration of silver will be twice that of the solubility. So that's why we have 2 times the amount that dissolves, the solubility amount, 6.5 times 10 to the negative 5. Following that, right? So just basic stoichiometry. If 1 molecule dissolves, or I shouldn't say molecule, it's an ionic compound, but for every 1 equivalent that dissolves, we form 2 units of the silver, and the chromate concentration is equivalent because that's a 1-to-1 ratio, right? So that's really basic maths. Just making sure you understand that for every 1 unit that dissolves, how much are we going to produce in terms of each ion? We need to look at the stoichiometric ratios. And the 500 mils doesn't matter because we're looking at concentrations. It doesn't matter if we have 500 mils or if we have 10 liters. The concentration will be the same because concentration is in moles per liter. So that's really basic maths. But often in the real world, when you're talking to people about concentration on the street, because you probably get asked this all the time, you know, what's the concentration of lead in my drinking water right now? They don't want you to report units of moles per liter. What's a more common unit for concentration, guys? Yeah.
Yeah, like grams per liter.
Yeah, grams per liter. That's my next question. So can we convert that same solubility from moles per liter to grams per liter? And thinking back to level 2, what's our favorite equation from level 2? Well, you might have a different favorite equation, but we all have favorite equations, right?
What?
Yeah, this is probably my favorite.
Cool.
Although I do like the volume one.
We're using this equation, and of course we got to rearrange it. I know it's rearranged on the screen. So, all right. Because we have units of moles per liter, we got to change that up. We know concentration is equal to N over V, right?
Mm-hmm.
That's my second favorite equation. C is equal to N over V. Maybe we could combine both of these equations to solve this problem in one step, right? We could substitute this equation for N into there. That'd be nice. Let's do that. So C is actually equal to mass divided by molar mass times V. See how I substituted that in? Sounds good? Cool. So now let's plug this in, and this will give us concentration in grams per liter. So the mass, what am I doing?
Number of grams in a liter.
I don't know either. What am I doing?
Molar mass.
We need the molar mass.
This is a fantastic stuff.
Grams per mole.
Oh, I know what I did.
It's 332. You did a foolish thing?
Unbelievable.
Unbelievable. We don't trust you anymore.
You trusted him and he's lied to you every year about the formation of, like,
Well,
why?
why?
I was even more. I looked at my sister's our textbook for chemistry, and for talking about electronegativity, they didn't just be like, look at fluorine and it's based off of that. They were just like, the further to the right it is, yeah, it's most likely electronegative. I'm like, it's not that hard to say it's based off of fluorine, guys.
It's just,
Okay, I fixed it. Because we want concentration in grams per liter, right?
Mm-hmm.
Yeah.
We want to go from moles per liter to grams per liter, and to do that, I plugged in what M is equal to in terms of moles times molar mass.
yeah.
So we know this. We know what N over V is because that's just the solubility number. It's the number 6.5 times 10 to the negative 5 moles per liter.
Oh no,
And then your times of that by 332 grams per mole.
I think he knows what he's doing.
really? Because you messed it up the first time.
There we go.
Once again, people, why are we trusting the man who has lied to us year after
So
year?
you replace mass with the equation. That equation.
That's what I want. I replace it with the equation, plugging in what I know already, right? That makes more sense. And look at this. Unit analysis says I'm correct because here's my solubility in moles per liter. By multiplying by the molar mass, Look what cancels out.
Moles.
And we are left with grams per
Grams
liter.
per liter.
There we go.
Whoa.
So unit analysis is useful. Okay. So the limited solubility converts to 0.0216 grams per liter. Cool? So very little. This makes sense. If you get a really large number, that's a way of checking your work. You know, you did something silly there. Last thing I want to talk about before we do some practice problems here is actually writing out the equilibrium constant expression for sparingly soluble solids. So we referred to that equilibrium constant as Kc last year. For this specific type of scenario where we're studying sparingly soluble solids, that alliteration of that letter S gives you a clue, we call that constant K sub S, okay? Because we're talking about sparingly soluble solids. So it's the equilibrium constant associated with these types of solids. So K sub S. Now for any equilibrium equation, we can write the corresponding mathematical expression, right? And notice there's no denominator in this expression. That's interesting, because we see in the equation, in this case of calcium hydroxide, it's in equilibrium with calcium ions and two equivalents of hydroxide ions. So we have reactants, we have products. Why isn't calcium hydroxide included in the equilibrium expression?
Because it's solid.
It is a solid, and that's one of our rules. So our expressions, they're actually easier, I think, than what you do at level 2, because there's no denominator to worry about. There's just a numerator. It's just one long line, right? You're multiplying the concentrations of your two ions that are the products of this dissolving, making sure they're raised to the appropriate power, and that's your expression. It's nice and short. Cool?
What? But like, so okay, now, so in the other one it was just Kc equals, and you were trying to figure out, like you would put calcium hydroxide?
Yeah.
Ella, I get it, and if you keep talking, it's going to confuse me.
Because Kc, you know, is a ratio of products to reactants.
So it doesn't matter. No, but what is she asking?
I know what she's asking. Just hold on, Angela. Ella, you were just about to say, you know that. Do you want to continue? You know that.
Yeah, like where in that equation it says like it's equal to that you would usually put that underneath for the thing, but is it because you're trying to figure out that is the thing that you're trying to figure out in this one, rather than it being part of the equation?
Yes.
Yes.
This is going to tell us.
Yes.
Just say yes.
Okay.
Yeah, it's because it's the solubility equilibrium of that thing.
Yeah.
Yeah.
Like delta H VAP or whatever.
Cool.
Yeah, cool.
So what we're going to do in just a minute is I'm going to give you a few practice problems where you need to do the following. You're going to have to write out the balanced chemical equation with those double directional arrows, right? And you'll need to write out the corresponding equilibrium expression that matches up with that equilibrium equation, okay? Raising everything to the right powers, remembering that solids are not included in the expression, so there's no denominator. That's kind of quick and easy. So really, your expression is going to be correct if your equation's correct, if you've balanced it correctly. So balancing is the one tricky part to get the appropriate powers for your expression. So we're going to do the following 4 practice problems now, and then we'll take those up in a few minutes. So you have calcium carbonate, you have silver sulfide, you got lead iodide, you've got iron hydroxide. You need to write the equation for the solid dissolving, write the solubility product expression, and there's a third thing I want you to do. I want you to calculate the concentration of each ion. Remember, there's only 2 types of ion for every ionic compound, a positive one and a negative one. So using the stoichiometric ratios, I want you to use these solubilities to figure out the concentrations of those ions. So 3 things, 4 questions. Sounds good? Any questions?
I haven't been able.
Cool.
I'm just gonna do it.
I'll circulate around as you work on these 4 problems.